Okay. Y'all okay? Is it the door handle? Chat up and going. All right, with time to spare. All right, so attendance is open if y'all want to go ahead and check in on attendance. I guess I should kind of leave that up, then people know attendance is going. Let's double check that this can work. Hey. Well, 2 on that one. I guess my watch is 1 minute fast. I don't know about y'all, but I could really use a fall break right about now. It's too bad we don't get one. I empathize with you is what I'm trying to say. I wish I was a fall break. Yeah, it's been a long, it's a short semester, but I feel like it's been a long semester just because we haven't had breaks, and the breaks that we've had have been pretty high stress hurricane situations. So
I'm looking at the lecture schedule. You dropped the lowest grade in here?
I'm going to talk about that in just a second. I'm going to talk about that in just a second. I just changed that this morning.
Okay, I checked it like yesterday
No, it's
and
new.
I wasn't there.
It's new. It's new. All right, so how y'all feel about starting with a joke? I feel like y'all are gonna like this one, and this is a really great one for my son. So, what is the most common surgery at the Lego Hospital? Plastic surgery. That's cute. Y'all know how many Legos I've stepped on? Ooh, Legos hurt. All right, so if you have not done so already, please go ahead and do your iClicker attendance. And I have a few things that I want to talk to y'all about. So number one, we're going to finish chapter 7 today. So homework for chapter 7 will be due on Monday at 9 p.m. Okay. Anybody have any issues with the homework program so far? Are you doing okay? All right. Next Tuesday, we have exam 3. So just like we've done in the past, on Moodle, on Respondus, make sure that you have a good internet connection. Do not take it in the dorms. Please do not take it in the dorms. Come here, or there's a computer lab over there, but please, please, please make sure you have a good internet connection. Okay, very important. So the other thing that I wanted to talk to y'all about is I am going to make a change to our grading setup. I am going to give you a 4th exam, but I am going to drop your lowest exam score. So instead of just having 3 exams to take, you'll have 4 to take, and I'll drop the lowest one. So we'll still end up with 3 exam scores contributing to your overall grade, but you can have a bad day, and you can drop one. Does that make sense? So what we're going to do is, if you go to the calendar, which is right here, I updated the calendar. We can zoom out. Here we go. Okay. So if you scroll over, what we're going to see is we are right here on Thursday. Monday, our chapter 7 homework's due, and then Tuesday we have the exam, right? And I will have the exams graded, and you'll get your results on Tuesday, so that if you are thinking about dropping, you will have all the information that you need in order to make that informed decision before drop day, okay? So I'll make sure that all the grades are out. Okay, so then we'll do chapter 8. Now look, there's gonna be a change in when your homework's due. Instead of being due on Monday, then for the rest of the semester, it's gonna be due on Wednesday, because we'll have part 1 lecture on Thursday, part 2 on Tuesday, and then homework's due on Wednesday. So you don't have the whole weekend to complete the homework. So you need to not let that wait until Wednesday night, okay? So then we'll do chapter 9. Chapter 9 homework due on a Wednesday, chapter 10 homework due on a Wednesday. And then on that Thursday, that will be our 4th exam, but you can drop your lowest regular exam score. So if you are happy with your first 3 exams, you don't have to take the last one, right? But you have to take the final exam. So depending on what section, and we are 4T, so our 4T exam is on Thursday at 1 o'clock. So really close to our normal class time. But on exam week, 1 o'clock in here, and it will be on paper. So your final exam will not be a, somebody in the chat. Okay, I'm gonna answer questions about that, Jacob, in just a second. So our final exam will be on paper in this room, right here, on Thursday of exam week at 1 p.m. Okay? If you have any questions or concerns about it, you can send me an email, but that is the plan. Okay? Any questions? How y'all feeling? Feeling good about a dropped exam? I thought that would kind of make y'all a little bit happy, huh? So I have to go in and I have to reconfigure the gradebook so that I can make that drop happen. So the gradebook's going to look a little different, but I'm going to have some help because I'm not very good at Moodle. So I'm going to have another professor help me out. But is the final and everything? Yes. The final is a cumulative final exam. Cumulative final exam. Always was, always will be. Cumulative final exam.
How many questions?
It's a 2-hour long exam. So I don't know how many questions because I haven't written it yet, but it is planned to take you 2 hours. Like I normally plan for your exams. I give you 70 minutes to take your exams. And so I plan it for that amount of time. So it's 1 hour and 10. So it will be longer, but not quite double. Not quite double. Yes, ma'am.
Will it be weighted more? Or will it be the same on the regular?
No, it's weighted more. So if you go to the syllabus, it's weighted like twice a regular exam. So look. Under the final. Oh, are they, Jade? I mixed them up. Okay, I will fix it, Jade. Thank you. And Laura, the calendar, it says Thursday. Yes, it's supposed to be Thursday for 4T. I don't know how many questions are going to be on the final exam yet. Okay, so where is it? Did I pass it up as I was looking at the chat? I think I did. That's what happens when you try to do multiple things at once. Here we go. So your regular exams are 100 points each, and then your comprehensive final exam is 200. Okay, so it's double. It's double. Okay. All right, so, and I will go in and fix, let me see, where was that? Let me edit it and fix it real quick so that it's right. On the final exam, oh yeah, I do have it wrong right there. I see it. The final exam covers chapters 1 through 10. That is correct. That is correct. Okay, the 5T, 4T. Okay. Thank y'all for noticing that and letting me know. Okay. So did I answer everybody on the chat? Moodle, it says 4T. That's for 4T. So we are 4T. We're going to start at 130 to 250. Oh, no, I'm sorry. Oh, I have that. Oh, my goodness. I have that all wrong. Hold on, y'all. Let me make sure this is right. This is, this one goes here, and this one goes here. Sorry, y'all. Okay. Yep, that's right. Final. All right. If I make any other mistakes, please tell me. I will fix them. All right. Any other questions before we start? Okay. So let's go do some clicker questions. All right. Chapter 7. Move this over. Nope. Why is it blank? Where did it go? Oh, goodness. I figured everybody would be happy that I'm dropping a test. I figured that would not be a problem. Let me close all this other stuff. Okay, I don't understand. I'm seeing this one. Where did it go? Y'all, this is crazy. Okay. Let's try this a different one. More than one way to make it work. Yeah, 109's covers more topics. It does. Is this opening? Bless you. Okay, now let's try this. Okay, here we go. So here's our first iClicker question. Which relationship is inverse when one increases, the other decreases? Okay. Okay, Jordan, I see. So, yeah, just turn it off and turn it back on. It's at 1.5 minutes, I'm gonna call it. Five seconds. All right, so what did we say? Which relationship is inverse? What equation did you use to help you answer this? Pivnert, PV is equal to nRT. So if you have two variables on the same side of the equation, that means they're inversely related. So if we increase volume, what's going to happen to pressure? Going to decrease pressure. So which one had our, what are we saying? Should be pressure and volume. So it should be G. D. Why did I say G? D. Okay, good. All right, so let's try another one. A sample of gas in a 1 liter container at 1 atm, let me move my talking thing, of pressure is placed into a larger container. What happens to the pressure? Ten seconds. Okay. So what did we say? What happens? If our sample of gas in a 1 liter container at 1 atm is placed into a larger container, so what happens to volume? Increases. So tell me what's going to happen to pressure? Decreases. That's what we just said. So your pressure should decrease. That should be A. Very good, y'all. Very good. All right. A gas sample of 1 liter at 25 degrees Celsius is heated to 50 degrees Celsius. What happens to the volume? And I don't have a study guide for the final. I do not.
So it's just all day class problems.
Yeah. I'll talk to Dr. Smith and see how he usually does the end of the semester. I'm not sure. So I'll get back to y'all on that. No, we are not going into partial pressures in class. Can't cover it all. Got to draw the line somewhere, right? You're like, yes. Yes, please. Ten seconds. Okay, so what did y'all say? You did Pivnert, right? And what happened to temperature? 25 to 50. We went up. We actually went up by how much? It doubled, right? It doubled. So if we want the two sides of the equation to be equal, what's going to happen to something on this side? It's going to have to go up. So our only choices really were volume. So volume's going to go up. How much is it going to go up? It's going to double. Okay, so what did y'all say? Good. Yay. All right. We'll do a few from here. All right, so this one's from lecture. This one's from lecture. What change of state occurs when frost forms on car windows on a cold morning? Not that it happens very often here, but it does. So what change of state occurs? Ten seconds. Okay. So what did we say? Oh, good. Deposition, deposition. So when you're going from frost, when you're forming frost, what's that transition? What are your states of matter? You're going from a gas to a solid, right? Because the water's in the air and then it forms ice on the car windshield. And so that is your gas to solid transition. So you should have said C, deposition. Did I? Yes, great. Okay. All right, one more. What happens during vaporization? What happens during vaporization? Okay, 10 seconds. Okay, so the two choices are two big concepts. A and D say covalent bonds are either broken or formed, and then B and C are talking about intermolecular forces. So can we narrow it down from those? Do we have covalent bonds changing when we change states of matter? Absolutely not. Absolutely not. Bonds are not formed, bonds are not broken, ever. So you can completely cross those out. Now, B and C both talk about intermolecular forces. So when we go from vaporization, what's happening in vaporization? It's going to a gas, but what's it starting out as? A what? Are you going from a more ordered or a less ordered? You're going from more ordered to, I'm sorry, yeah, to less ordered. So even if you're going either from a gas, from a liquid or a solid, doesn't matter. Are you going to disrupt bond forces, or are you going to create intermolecular forces? You're going to disrupt them, right? So anytime you transition from more ordered to less ordered, you're going to have to disrupt some interactions between those molecules. And when you disrupt those interactions, then that's how you're going to overcome being in a tightly organized fashion to being in a gas that's so far apart and all the way away, right? So you should have said B. Should have said B. Okay. All right. So let's go and do some ICP stuff. And then if we have time, I have a few more that we can pick up to boost our clicker scores. So I think we left out on 7.30, is that right? Yes, we finished 2.8, so we should be on 3.0. Okay. Yeah, what? We did 3.0. Okay, so we have to go to the next one. Okay, I didn't write that in my notes. Okay, so we're on 3.2. Rank the following compounds in order of increasing boiling point, lowest to highest, and explain your ranking. All right. Before we decide which one's going to have the highest and lowest boiling point, what are we organizing them based on? Like what substance is going to have the lowest boiling point? And what's going to have the highest boiling point? Not of these three, but like in general. What kind of substances are going to have low boiling points and what kind of substances are going to have high boiling points? Stronger versus weaker, that's right. So which one's going to be stronger? Strength of attraction, that's exactly right. The higher the boiling point, the stronger the attraction. Lower boiling point is weaker attraction. So we want to order from increasing boiling point. So we want to order from weakest to strongest. So let's label these A, B, and C. Tell me about A. Anybody know what functional group that is? That is an ether. That is indeed an ether. That is indeed an ether. Okay, so in an ether, we have an oxygen. You know what's kind of weird about that oxygen? Looks to me like it doesn't have a complete octet. What can I add to this drawing that might help my understanding of intermolecular forces? Lone pairs, right? Okay. So we have A is an ether. What's B? An alcohol. What could we do to this one? Does that oxygen have a complete octet? Okay. So we're going to go ahead and give it a complete octet. And C, what is C? It's a straight chain alkane. It's a straight chain alkane. Okay, so let's talk about the forces that each one can participate in. How about A? What kind of interactions is A going to have? What kind? So what do you need for hydrogen bonding? You need a lone pair on no fun. We have that. What else do we need? We need a hydrogen bound to what? No fun. We need a hydrogen bound to no fun. Do we have a hydrogen bound to no fun? No. Okay, so what do we have here? Well, they're all going to have London dispersion. So they all at least have London dispersion. Do we have anything else going on with molecule A? Polar or nonpolar substance in A? No, this is going to be polar. This is going to be polar. Remember how water, if you had the oxygens, they actually get drawn like this, right? Well, it's the same thing, except instead of having hydrogens, guess what we have? We have carbons. Same thing. So if water's polar, this is polar. Okay? All right, so if it's a polar molecule, what kind of interactions do we have? If it's polar, we have dipole interactions. Because how do we know something is polar? It must have a dipole. So if one molecule has a dipole and it interacts with another molecule that has a dipole, we call it a dipole-dipole interaction. That's where the name comes from. So by definition, a polar molecule must have a dipole. And so you have to think that you have just this pure substance, right? So all you have are these same ether molecules over and over and over again. And so they can interact with each other through dipole-dipole interactions. How about B? Now B can have hydrogen bonding. Hydrogen bonding is a stronger form of dipole-dipole interactions, right? Is this a polar molecule in B? B is a polar molecule. Definitely it's polar. So it could interact, it could have dipole-dipole interactions, yes, but the strongest of those is hydrogen bonding. And we see that it has a hydrogen attached to an oxygen, so that gives us the donor. And then we see that it has two lone pairs. Well, that gives us two acceptors. So it can participate in hydrogen bonding with another molecule of itself. Okay. All right, how about C? Is it polar or nonpolar? That's the first question you want to ask yourself, polar or nonpolar? This is nonpolar. If it's nonpolar, what do we only have? London forces or London dispersion. Okay, so let's rank these from smallest attraction to largest attraction. So what's the smallest? The weakest attraction, so it'll have the lowest boiling point. C, then what? Then A, then B. So London forces are the weakest. Then we have what? Let's order them. We go London's the weakest. What's the next strongest? Can we write this up here? Let's see. If we have London, then what? Then we have dipole-dipole. Then what? Then what? Ion dipole. Then what? All Ionic interaction. You need to know that. This might be another one of those things that you write on your scratch paper as soon as you can. Good. Okay. All right. Moving on. Okay, 2 common inhalation anesthetics, desflurane and halothane, have boiling points of 23.5 degrees Celsius and 50.2 degrees Celsius, respectively. Which one is predicted to have the higher vapor pressure at a given temperature? So tell me about vapor pressure. Before you try to answer it about 2 substances, you need to think about vapor pressure. So if you have a low vapor pressure, what does that mean? You have a high boiling point, you have a high melting point. Why? Exactly right. Oh, y'all are on the ball today. Do you think these kinds of molecules that have low vapor pressure, high boiling point, high melting point, do you think they have strong attraction or do they have weak attraction? Strong attraction or more attraction, right? That's what we kind of said yesterday. Okay, so now let's look at our 2. If we have a boiling point of 23.5 and then a boiling point of 50.2 degrees Celsius, right? Of halothane. Okay, so which one is going to have the higher vapor pressure? Higher vapor pressure, higher vapor pressure. So if you have a high vapor pressure, what do you have? A low boiling point. Okay, so which one has the lower boiling point? The first one. So write yourself that stuff down when you've got your scratch paper. Write it down. Don't be afraid to write it. All right, so we're going to change gears. We're talking about solubility. So solubility is all based on interactive forces, right? And so now you know all about those interactive forces. Now let's talk about solubility. In order for something to be soluble, water must completely surround the molecule, okay? So how do you get water to completely surround the molecule? What's your little saying for if we know something is soluble or not? Like dissolves like. Like dissolves like. Keep that in mind. Always go back and think about that. Like dissolves like. So if I want water to surround something, what kind of an interaction can water have with any molecule? Hydrogen bonding, right? It can participate in dipole interactions, but hydrogen bonding is going to be the best, right? So if you have things inside of your molecule that can participate in hydrogen bonding, they're going to be very soluble molecules. So number one, we want as many parts or functional groups, right, that can participate in those interactions. We want as many as possible, and we want them kind of dispersed throughout the molecule. You don't want them all on one side, because then it's not going to be completely soluble. Okay, so that's our two things we want to think about. All right, so based on their polarity and attractive forces, predict whether the following compounds are soluble, insoluble, or form a micelle. What was a micelle again? That little bubble, right, that gets formed because you have one side of the molecule that's polar that can interact with water, and then you have the other side of the molecule that's nonpolar that doesn't want to interact with water, so it ends up hanging out with other ends of the same molecule. So you end up with basically a bubble, and the outside interacts with water, and the inside, the little tails interact with each other. So this is how soap works, right? You'll never think about washing your hands the same way again. Now you understand why it works. It's kind of cool. So NaCl. What do we think? Yeah, if you put salt in water, what happens? It dissolves. Use your common sense. You can use that too. It's a good thing to use in combination with your science knowledge. So this one is soluble. Now, why is it soluble? Now you're going to have to draw on your science knowledge. Yes, you know salt dissolves in water. Why? What is salt? It's like a sodium atom and a chlorine atom, right? And they alternate. And you have this ionic crystal, right? Are each of those individual things neutral? Those individual atoms, are they neutral? No, they're not neutral. They're charged. So one's going to be plus, one's going to be minus, right? Plus, minus, plus, minus, plus, minus, plus, minus. So what happens when you put this into water? Exactly right. Yeah. So if we have a negatively charged particle here, and I have water, what's going to happen is my hydrogens that are partially positive are going to want to interact with that negative. And so what ends up happening is you have water molecules that just surround this negative. Same thing happens over here, right? HH. Get your lone pairs. So your partially positive hydrogens are going to be interacting with the negative. And vice versa. What happens if you're a positively charged particle? The oxygens are going to want to interact and the hydrogens are going to stick out. Right? So the water molecules will just orient differently. But that's why salt dissolves so well in water. Okay, went off on a tangent there. Sodium stearate, 18-0, a fatty acid salt. If it's a fatty acid salt, what's a fatty acid salt? You have like an ion, like sodium plus, and then what do you have? This is the salt part, so then you must have a negative. If it's a salt, you have to have a positive and negative, right? A salt tells you you have a positive and negative, just like NaCl. Na is positive, Cl is -1. What else do you have? What's in a fatty acid? An oxygen to a carbon to a carbonyl, right? And then, right, you remember all this? Yeah, okay. So soluble or insoluble, what do you think? Well, what's this portion? Polar or nonpolar? This is nonpolar. Yes, on chat, they got it on chat. So this portion is polar. So if you have one section of the molecule, and really I should have kept going because it's 18, so it's really long. But if you have a nonpolar region and a polar region, what are you going to form? You're going to form sodium stearate, a fatty acid, yep. You're going to form a micelle, C-E-L-L, micelle, okay? So if you have that nonpolar and polar, what do we call that? That's what kind of a compound? Anybody? Looking on the chat? Amphipathic? A-M-P-H-A. Amphipathic? I can't spell. But that means it has partial positive, partial negative. Okay, last one. Isopropyl alcohol. Isopropyl alcohol is soluble. Why? What does it have in there? It has an alcohol. And alcohol can participate in what kind of bonding? Hydrogen bonding. How are we doing on this? I'm not feeling too good about this. Y'all got to practice these. You really got to practice these. This one, you might want to go in the back of the book and try some of those extra problems. Okay. All right. Predict which of the following compounds is likely to be more soluble in water. Justify your answer. So we'll say 1 or 2, and then 1 or 2. So in A, what do we think? 1 or 2? Anybody else? 1 or 2? Like, this is the eye doctor. 1 or 2, 3 or 4. 1, everybody on the chat's giving me a 1. Okay, that's right. So CH3, CH2, OH is more soluble. Why? Yes, it has an alcohol, which can what? Okay, good. All right, in B, 1 or 2? Can I get a few more people in the chat at least? 1 or 2? 1. Why 1? This is B. Because why? Because of the nitrogen. Okay, so it's not just having an oxygen present that will allow you to participate in hydrogen bonding. If you have a nitrogen and we have hydrogens attached to that nitrogen, guess what? We got hydrogen, we have hydrogen bonding. Remember, no fun? What does that N stand for? Nitrogen. Because it has, right, a nitrogen with lone pairs and a hydrogen bound to a nitrogen. So it can participate in what? Okay. You have to be able to look at these molecules and say soluble or not. You have to. So you need to go and practice that. Absolutely, you need to go and practice that. All right. Now, we're going to apply that knowledge to fats that we encounter in our everyday lives and dietary fats. So lipids. All right. So what's in a triglyceride? What does tri refer to? 3. Now, glycerol. How many remember from the video? So the 3, that's a good thing. The 3, what is it? It's 3 what? Good point. Fatty acid tails. Fatty acid tails. And then we have a glycerol molecule. So what's a glycerol molecule? 3 carbons, right? Those 3 carbons are each going to be bound to an oxygen. Now, in glycerol itself, this would be a CH2, this would be an H, this would be a CH2. You would have a hydrogen there, right? And that would be glycerol. But we're saying that this is a triglyceride, so we have to add that fatty acid to it. So when we add that fatty acid to it, now in a fatty acid, you have an oxygen, right, bound to a carbon that is in a carbonyl bond, and then we have a fatty acid tail, right? You have to know the basic structure of a fatty acid. Okay, same thing. We just do it 3 times because it's a triglyceride. So we have 3 fatty acid tails and 1 glycerol molecule. So look at the name and use it to trigger what you remember. All right. Now let's talk about some specifically. Olive oil is a mono unsaturated oil. What does mono unsaturated mean? It has one carbon-carbon double bond. Soybean oil is a polyunsaturated. What does polyunsaturated mean? Poly meaning many, and unsaturated meaning carbon-carbon double bonds, right? Because if it's saturated, it's covered in what? It's covered in hydrogens. And if it's not covered in hydrogens, we still have to complete the octets. So how are we going to complete the octets? We're going to give it double bonds. So don't forget that. Okay, so our olive oil has a melting point of -6, and our soybean oil has -16. Explain their difference in melting points. Anybody want to take a stab? What happens when we get more carbon-carbon double bonds? What does that result in? Kinked tails, right? So they can't line up perfectly one on top of the other. They kind of get bent and out of shape, right? Well, if I have something one on top of the other, you have nice surface area contacts. But if I start bending things, how much surface area contact do I have now? Much less, much less. So kinked tails tells us less surface area, right, area contacts between the tails. So why does that matter? Why does surface area matter? The more surface area we have, more what? What kind of forces exist between all substances? London forces. So the more surface area you have, the more likely you are to bump into one another and disturb those electrons. That's what London forces are. So the more disturbed electrons you have, the more London dispersion forces you have. So this is the opposite, right? If we have those kinked tails, we're going to have less surface area between our tails, which results in what? Weaker or less London forces. So tell me, how is that going to, we got to get to melting point. How does that affect melting points? The weaker the forces, let me extend the page. The lower the melting point. That's just saying that you don't have to get to a very high temperature to turn it into a liquid, right? You don't have to put a lot of energy in to disrupt those interactions, because there aren't that many to start with, because you have all those kinked tails, right? Our carbon-carbon single bond, right? You would just write the opposite. If you have less carbon-carbon double bonds, you would have straight tails, right? Fatty acid tails, ILS tails, right? So you have what? More surface area. So you have stronger London forces. Stronger London forces means a higher melting point. Right? It's going to put more energy. That's what temperature is. It's a measure of energy. So you'd have to put more energy in to turn this into a liquid. Yeah? Okay. All right. I'm gonna go up here. We're almost done. We're gonna be able to get some more clicker questions in. Excited. I'm excited. No, I'm not excited. All right. One of the main triglycerides in palm oil is Palmatin. It contains 3 fatty acids with carbon designations of 16-0. Draw the structure. Would you expect this molecule to be solid or liquid at room temperature? Let's draw it first. It is a what? A triglyceride. So let's start with a triglyceride. I'm going to put my carbons over here this time. Always put the same thing. We're going to be bound to an oxygen, right? We got to give this enough hydrogens to complete the octet. So then that oxygen is bound to a carbon, and that's our carbonyl carbon. So it's double bound to an oxygen. Now, do you remember what this 16-0 designation tells us? So it tells us, I know I'm going to get in trouble if I do it down here. Let me do it up here. So this 16 is equal to the number of carbons. And then 0 tells us our number of carbon-carbon double bonds. So when you do this, you have to be very careful about one thing. You count your carbon in the carbonyl bond. Lots of people make that mistake. Do not make that mistake, okay? So I've already drawn my first carbon. Right here, that's my first carbon. So now I need to go until I get to 16. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then if you were going to count them, because you might have to do this, where would you start counting to make sure that you did it right? You start on the carbon farthest away from the carbonyl. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I know I'm good. Always go back and double check to make sure you have the right number of carbons. Okay, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16. Same thing here. So it's already 1, 2, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16. And if I were a great artist, they would end up in exactly the same place, but I'm not. All right. So next question. Would you expect this molecule to be a solid or a liquid at room temperature? And why? Okay. So we expect a solid. Why? That's exactly right. This is a saturated hydrocarbon. So we have lots of surface area contacts. More surface area contacts tells us more London forces. So what will it have? A higher melting point or boiling point, however you want to, whatever you want to think about. Melting point / boiling point. Last one. Almost done. All right. So now we talk about the cell membrane. Now, they didn't have very many questions on this, but make sure that you understand how phospholipids work. How are phospholipids different than triglycerides? So a phospholipid has only 2 fatty acid tails, right? That's correct, 2 tails. And what about the phospho part? So here's a tail, that is 1 tail, there's 2 tails. So then tell me about the phospho part. This is a phosphate, P-H-O-S, oh my goodness, my brain. This has a phosphate group, and it is a polar, it's a polar part, and so we call this the head group. Head group, and it's negatively charged. So all of these want to associate with water. All of these want to associate with water. And then everything in the middle, all of these fatty acid tails are non-polar, and they do not want anything to do with water. And so they end up hanging out with each other instead of hanging out with water. So up here, you have a cells, everything with the cells sitting in, all the extracellular stuff, which is mostly water. And then on down here, this is the inside of the cell. This is the cytoplasm, mostly water. So that's why we have lipid bilayers, so that we have that separation between external environment and internal environment. Okay. Draw a possible hydrogen bond between a molecule of cholesterol and a molecule of water. I'm telling you on the exam, you're not going to have to draw cholesterol, right? It's multiple choice. You might have to identify one that is cholesterol or not. So what's, there's something common between all cholesterol molecules called the steroid nucleus. So our steroid nucleus is a lot of these rings, right? We have another ring, draw this correctly. And then this ring shares with the one above it. I could do that. Okay. And then you have a house. That's what I call it. I call it a house because it doesn't, one less carbon, so it ends up looking like a house. And that's pretty terrible, but that's the steroid nucleus. I am not the best artist, I will admit it. You know, that's why I kind of like that homework program that y'all have, because it ends up making all your drawings look really nice. All right, and then you've got a carbon coming up here, and you've got a hydrogen coming up here. So just try to give you dimensional, and then a carbon here. All right. Okay. So that's your steroid nucleus. So now all of your steroids are going to have that basic structure and then some other stuff attached to it. So in the case of cholesterol, we have an OH group here, and then we have a bunch of carbons up here. Another one coming down, and then another little Y. So you got a lot of carbons coming off of one end. So tell me, where can this interact with water? Only on one side, only over here by our alcohol, right? So how many different bonds, I shouldn't have circled that, how many different hydrogen bonds can it participate in? Well, it says, draw a possible hydrogen bond between a molecule of cholesterol and a molecule of water. So how many hydrogen bonds can this alcohol participate in? So I could do it with either one of the lone pairs, right? And that would associate with a hydrogen from water, right? What else? The H can be a donor. So it would participate, let me see. I guess I shouldn't have drawn the water in the same thing, but that's okay. So the hydrogen from the steroid can participate in a hydrogen bond. So I can have 1, 2, 3 different ways to answer this question. It really said just to draw 1, but I wanted to know how many possible, and there are 3. Okay. So a lot of times you'll see cholesterol inside of the membrane, and only one side of it will be exposed to the aqueous environment, and all the rest of it, look at all this stuff up here, this stuff is all going to embed inside of the membrane. And so this will actually change the viscosity of the membrane, right? So have you ever seen, I should have brought a little animation. Have you ever seen an animation of the plasma membrane? It's really kind of cool because you have this, it looks like a solid membrane, and then you have all these proteins and stuff, and they just like float inside of the membrane and can move all around, and it's really cool. If you Google like animation of, it's called the fluid mosaic model, and it's a really cool animation. I should have brought that. I didn't think about that. All right, so I was hoping we would finish early. So I thought we could bulk up on our clicker questions. Oh, that clicker question wasn't working. No, this one is. Yay. Okay. Did that. We did that. Okay, y'all ready? Yeah? Okay. Which force is the weakest? But y'all might like this. We just covered this. Should be some good clicker points. Try to get y'all up to 70%. I think we've dropped off on people. Maybe not. A minute and a half. Okay, 10 seconds. I think it might be. All right, so what force did y'all say is the weakest? Oh, that's so awesome. I love seeing that. Oh my gosh, I love seeing that. Oh, and then I'm gonna have to go back and fix that because I messed that up. All right, now, which force is the strongest? Y'all glad I saved these for the end? I thought y'all might like that. Because next time I see you, it would be an exam. So I can't give you the clicker questions on that. I know, right? Yep. The next time I see you, it's an exam. I know. So if you have questions, make a Zoom appointment, send me an email, something. I think 63 is our max. I do. I'm still gonna wait the minute and a half because that's what I said I'd always do. Oh, 64, look, see? It's a good thing I waited. I'm gonna wait the minute and a half. Y'all want another joke? Because y'all did so well. All right, what are Lego figures' favorite dance? Square dancing. I had to find some jokes for my son, so you know. I'm trying. If anybody's got a good joke, they can put it in the chat. All right, so what are your strongest forces? What did y'all say? Good. Good. Our strongest forces are our ionic attraction. Ionic attraction. All right, so if you order them from weakest to strongest, we go London dispersion, dipole-dipole, hydrogen bonding, ion dipole, and then ionic attraction. So make sure you have that. All right, now you have to analyze a molecule. Which intermolecular forces of attraction form between HCl molecules? So all you have is HCl. There's nothing else there, just molecules of HCl. If you have to draw it, draw it. It's okay. Ten seconds. Come on, I know I had 64. Everybody click in. All right. Okay, so in HCl, what do we have? Hydrogen and chlorine. Tell me about this bond. Who's the most electronegative atom? Fluorine the floozy, right? You know chlorine's next door neighbor to fluorine the floozy, right? So pretty gosh darn electronegative. So tell me about this bond here. It definitely has a dipole, so we're going to point to our negative chlorine, and that's the only bond. So the overall dipole moment of the molecule looks like this. So we have a polar molecule, but do we have hydrogen bonding? No. So what did you say? You should have said, so we said not hydrogen bonding, not hydrogen bonding, not hydrogen bonding. So either dispersion only or dispersion and dipole-dipole. So you should have said dispersion and dipole-dipole for C. Very good. I have 2 more clicker questions for you. Whoa. I forgot on this one. I got to clear it. Where's my clear thing? I don't know. It's a struggle, man. It's a struggle. Come on. All right. So select the compound or compounds that form the strongest intermolecular forces of attraction between these 3 compounds. One of them is the same that we just showed. Okay, 10 seconds. Ooh, we're up to 65. 66, all right. So, do we have any, if we start at the maximum attraction, right? Do we have any ionic interactions, like NaCl? No, we don't have any of that, right? What's next? Ion dipole. Do we have any ion dipole? No, we don't have any ion dipole. What's the next one? Hydrogen bonding. Do any of these molecules participate in hydrogen bonding? Yes, A participates in hydrogen bonding. So this one participates in hydrogen bonding, right? What did we say HCl was? Dipole. Dipole. What did we say? This last one. How do you know that? If you have two atoms that are the same electronegativity, of course, if they're the same element, they have to have the same electronegativity. Do you have a polar bond? So do you have a polar molecule? No. Okay, so you should have picked A. Oh, we all picked B. See, but HCl is only dipole-dipole, whereas F2, London. And then the NH3 is hydrogen bonding. All right, y'all ready? This is going to be the toughest one yet. I have to clear it. All right, select the compounds that form the weakest intermolecular forces of attraction from these three compounds. Toughest one. Oh, I gotta open it. That would be nice, right? Yeah, I'd like to be able to click in on this one. The only one word changed, and it left the writing, so I figured I'd leave the writing for y'all. All right, you are free to go. I will leave it open for 1 minute and 30 seconds, as always. Good luck studying. When it closes in 1.5 minutes, I will tell you the answer. But if you know the answer, you are free to go. You can hang out for the 1.5 minutes. I have no idea. I think once you click in, I think, but I don't know for sure. See, y'all are so waiting for the dramatic reveal. Y'all have a good weekend. All right. So it should have been F2, which is your weakest. So it should have been C. All right, that's it. Anybody in the chat need anything? All right. If y'all have any questions, y'all can send me an email or set up a Zoom. Everybody good? Y'all have a good weekend. All right, I'm going to go ahead and end.